So in this section, we're going to talk about something that's very rare in inorganic chemistry, which is the ability to make predictions. Okay, and this deals with the reactions of square planar complexes. So the first thing to note about square planar complexes is that the main mechanism is an associative mechanism and not dissociative. And that's just because the square planar complex inherently has open space above and below the plane of the molecule for attack. So if we look at an example square planar complex here with a metal with 4 ligands, we're going to ignore 2 of them altogether. We're going to, as we see through these notes here, pay attention to this trans ligand, but right now this is our leaving group X. Okay, so we're being attacked by some incoming group Y, and that Y will attack your metal above or below the plane. So we're going to show this attacking above the plane like this. And what that will do is it will shift X downwards as Y comes in, right? It'll also simultaneously weaken the bond to the metal X and strengthen the bond to the metal Y. So this is that transition state where you're halfway in between. So the next step is that the X ligand will eventually leave, right? So we're going to lose the X ligand and we're going to be left with our metal complex. So this is just a simple associative mechanism, but the geometry of this transition state is really important. So this is a trigonal bipyramid shape. You can see these are the axial ligands, the ones that we're ignoring, and we have 3 ligands now in an approximate trigonal plane. Okay, and so this is going to affect how this ligand trans to the others influences the result. Mixing up some language we're about to use. So the first effect we're going to look at for this ligand, which is trans to the leaving group, is called the trans effect, and it's a pi effect. It's an effect of pi bonding in your metal complex. And so we know that some ligands are pi donors and some ligands are pi acceptors, and they both contribute to this kind of effect. So down here there's a drawing of the pi structure of in this case, a pi donor, but it's roughly the same in each case. So we see that these areas are where the pi bond is between the ligand and the metal, but that structure extends, if this is say a dxy orbital or something, that structure extends to these ligands, and these are all in the same plane. This is all part of this same sort of trigonal planar geometry here that we have for this complex. So whether we're pushing electrons in, as we would for a pi donor, into that complex, that can strengthen this bond, or if it's all going the other way, say we have a pi acceptor, which is pulling electrons from the metal, that will then allow the ligand to push electrons back in. So that effect will be stronger. The pi acid effect or the pi acceptor effect will be stronger than the pi donor, but they both do contribute. So if we looked at the effect that it'll have on the reaction coordinate diagram, this would be our original transition state for this, this complex here going through this associative interaction. And the effect of this stabilizing of the transition state is a decrease in that activation energy. It decreases the energy of the transition state. And so your EA, your activation energy here, is smaller than it would have otherwise be. So this stabilizes the transition state, and therefore it speeds the reaction. There's another effect, which is confusingly called the trans influence. This language here is just to sort of separate it out from the so-called trans effect, but it's another effect that the trans ligand can have, and always does have, actually. It's sometimes called here, this has the thermodynamic trans effect. But this has to do with the sigma structure. Okay, so your ligand here, whatever it is, must also be a sigma donor. And so if it is bonding really strongly with this metal, I drew this as a bold line, right? If it's really interacting strongly with that metal, whatever orbital it's interacting with, that will, by its nature, sort of occupy that metal's electron density, and it will always weaken the bond trans to itself. This is a sort of a universal truth. You only have so many electrons to go around. If you're bonding really strongly on the left side, it's really weak on the other side. So that's going to weaken the bond to X. It's going to destabilize this bond. And so again, in a reaction coordinate diagram, what that means is if you start with your energy of your complex, your Ml3X, by weakening that bond to your leaving group, what you're doing is you're destabilizing that complex. You're actually raising its energy, at least the energy of the bond that we're interested in here. Okay, and so by doing that, again, your activation energy is this barrier here. It's going to be smaller than it would otherwise be, and so therefore the reaction will occur quickly, more quickly. It'll be more labile, you could say. So this is exaggerated greatly, but this effect is complementary to the trans effect we just talked about. So putting those effects together, there's a series, sort of like the spectrochemical series, but there's a series of strengths of this directing ability of a ligand. These are always about that ligand, just as we were drawing, which are trans to the leaving group. Okay. So we're interested in this ligand, not the leaving group at all. But what's the effect of this trans ligand, and how will it push this ligand out, right? So very good trans directors are going to force the ligand opposite to themselves out, whatever they are. And sometimes those ligands can be very strongly bound, but again, this effect here is somehow favoring the loss of those ligands trans to themselves. So if we look at the list, it's a little bit mixed up compared to the spectrochemical series. That is to say that the pi acceptors are not always the only things at the top of the list. So the very best trans directors are the same as the very strongest field ligands, okay, cyanide and carbonyl. But you see right along with them are hydride, and this is ethylene, okay, this is ethylene bonding through its pi bond here. So this is an excellent pi donor, sorry, a pi acceptor. It's an excellent pi acceptor ligand. We'll talk about this more in the organometallic chemistry section. Hydride is a perfect sigma donor. It's the only perfect sigma donor. So this series here, the very strongest trans directors, are a mixture of this trans effect. These are pi acids, pi acceptors, and also the trans influencers, hydride being one of the best at that. So that combination there is just all the best of both worlds there, right? And so then we look and we see very good sort of sigma donors. This is also a little bit of a pi acceptor, as we talked about before. This is another excellent sigma donor, a methide group. And then here's a pretty good large ligand that's soft that can interact through probably a pi donor method, right? And if we look at the other end, it might help us, right? So down here we have weak bases, sort of water, but it's actually tied with hydroxide here, and these are just things that don't, they're small. They don't donate their electrons as well. They're pretty poor at pi bonding. You see right next to them is ammonia, which was right up near the top of the spectrochemical series. It was our best sort of sigma donor that we had, along with hydride, I guess. But it's way down at the bottom of this trans-directing series because, again, it's just kind of too small and it's only a sigma donor, and so it just doesn't have much of that trans influence to go along. If we look at the halides here, and actually I left off fluoride. Fluoride is tied down here at the bottom along with the others. We see that there's iodide is a better director than bromide, which is better than chloride, which is better than fluoride. And, again, if you think back to the spectrochemical series, iodide was the very weakest field ligand. But that was, in fact, because it's a really excellent pi donor. And so here the pi donor ability is working for us and not against us as it was in that spectrochemical series. So this is a little bit hard to remember, but you can definitely pull out some pieces. You can definitely keep track of your halides, knowing that they go in order, the largest to the smallest. Okay, you can definitely keep track of the good pi acids, the good pi acceptors are all near the top. Kind of confusingly, pyridine is way down here. And then, it's kind of in order of, you could say, base strength, sort of. Ammonia beating water. Yeah. So let's look at this through a couple of examples and think about how to use this. So first, here's an example of a complex where we have two different kinds of ligands. We have a carbonyl group and we have amines, three of them. And we have to think about where is the replacement about to occur. And so here's our incoming ligand, water. And so the question is, which ligand will it replace? And so what we need to think about is which of these are a better trans director. Is it carbonyl or is it ammonia? Well, carbonyl was the very top of our trans-directing series. So this is the best trans director. And what that means is it will knock out the ligand trans to itself. And so that means water is going to attack in that ammonia position. And so what we get is this palladium complex with the water ligand, the aqua ligand trans to the carbonyl ligand. Okay, it's a classic example. So let's take a look at another. So here's a tetrachloro complex. When you have a situation like this, it doesn't matter which one you replace with your incoming ligand. In this case, it's ammonia. So we get this complex, and now we have to think about what happens next, right? So if you look back in terms of the trans-director series, chloride is better than ammonia. Ammonia is right there at the bottom, second to last, really, in the series. So chloride beats ammonia. So that means that chloride is going to cause the bond trans to itself to be lost, which could be this ammonia, which would then get replaced by ammonia, and we can't tell, right? Or it could be one of these chlorides knocking out the one opposite to itself. And so what we see, I drew it upside down here, but what we see is that this chloride directed the loss of the chloride trans to itself, and so we get this replacement of this ammonia up here. Okay, so we end up with a cis complex of this diamine dichloroplatinum. Okay, so one more set of examples here. So if we have there can be some complications in terms of leaving group effects, because before we couldn't tell if we were replacing ammonia with ammonia, but now we could actually tell. So we have this platinum complex, the same as our intermediate before, where we have 3 chloride ligands and we have 1 amine, and we need to think about where this phosphine is going to go, right? So we know still that chloride beats ammonia, right, in terms of the transdirector ability. So that says that this chloride should kick out the ammonia. But it doesn't have to kick out ammonia. It could kick out a chloride. And so the question is, which is a better leaving group? Well, it turns out, amines are not great leaving groups. They're bound pretty well to the metal. And so chloride is more likely to be lost, all else being equal. So this chloride is pushing away the trans ligand to itself, but so are the others, right? So these two chlorides are also pushing out. So the phosphine is going to replace one of these 2 chlorides. I can't remember which one I chose. I chose the top one again. Okay, so here's our new phosphine that just came in, right? All right, so then there's a second step to this reaction. So another phosphine is now going to come in, and the question is, where does it go? So you look around and you ask, which of these is the best transdirector? And phosphine is pretty high on our list. So phosphine beats chloride, which beats ammonia. So phosphine is our best transdirector, so that means for sure we're going to knock out the chloride trans to it. So we get this result. Okay, so now our new phosphine ended up down here. So this is our final product of 2 phosphine replacements. But this first step was driven by the fact that it's better to knock out a good leaving group, all else being equal, than a poor one. So let's look at another case. Here we have a different starting complex. So we have only 1 chloro group and we have 3 amines. So the question is, where do we start? And again, just like before, chloride beats ammonia. So chloride is going to direct the first replacement. It's going to knock out the ligand trans to itself, and there's nothing equal to it. Okay, so this ammonia is the one that will be lost. So we replace that with phosphine. Now again, we look and see which is the best transdirector, and now it's the phosphine, and so it's going to knock out the ligand trans to itself, and we're going to get a replacement of that chloride with phosphine to give us this new phosphine. Okay, so you just follow the sequence, and it will guide you to the answer. It's pretty likely predictable. Of course, every time you have reactions, you can have mixtures of products, but this is pointing towards the most favored product.